the session of digital transformation. I will act as replacement chair because our main chair couldn't arrive to the conference. So our first presentation is constraints of the distribution for automotive systems, delivered by Robert Hartger. Please.
Correct. Thank you very much for the introduction. So digital transformation is the name of the session. I noticed there's smart cities, IoT stuff, face recognition, and automotive system here, so it's a rather broad range of topics. And this topic may sound rather generic, but I really digged into a very narrow research gap in this domain, what you will see shortly. So there are a lot of terms, especially when talking about automotive systems, because there's the AUTOSAR standard and many notations, many definitions. So I try to be precise, but not introduce too many notations, because this would rather consume a lot of time, I guess. So, well, this is the typical agenda. What research activities I've been doing in the past, what is the motivation behind it, what the actual problem is, how we solve the problem, and I also going to present some measurements, comparisons with the state of the art in the literature, and finally, of course, I have a conclusion slide. So, what is the motivation? Well, automotive system is a very specific domain, because we're talking about real-time, embedded, distributed, mixed critical, and heterogeneous systems. And this is a lot of things that comes together. For example, the scheduling and the real-time community, they have their conferences where they just have like the first 2 or maybe 3 of those specific demands, but the automotive domain combines a lot of topics together, which makes it specific and requires sophisticated solution and advancements to solutions that are already existent. And of course, the automotive domain is also, when talking about digital transformation, undergoing a kind of change, because all the engine management, they're changing because we were switching to electrification, electric vehicles, and so on. And of course, the automotive industry is targeting towards having autonomous driving cars in the future. And this I mentioned AUTOSAR, like the architecture that has been established many years ago. It's a common architecture across the big OEMs, the tier 1 suppliers, the tool vendors, and so on. A common standard that all the companies involved in the automotive domain are trying to, or are developing for. And there are even more standards like automotive spice, and of course they have legacy software from all the cars that they still want to reuse in modern cars. And this comes to a vast amount of requirements and constraints. In order to consider those requirements and constraints, sophisticated and traceable approaches to, for example, software to hardware mapping are required. And what actually the software to hardware mapping is comes on the next slide. And the challenge here is to incorporate all the constraints, and to not only incorporate them, but also to make them analyzable and verifiable against the constraints and against the requirements. So that it's for a developer or manager, it's clear and he can validate that a requirement is held in all kind of situations that can appear in a scenario, in a driving scenario. And there are also a lot of measurable metrics involved in such developments, like reliability, scalability, feasibility, predictability, and so on. So what actually is the mapping problem? So this is the thing that we tackled in our paper that we published here. Sadly, you can see hardly the colors, because there are actually a lot of colors. There's blue colors, yellow colors, and green. However, I'll just try to explain what this is. This is just an excerpt of car hardware. Usually you can have up to 100 ECUs, which stands for electronic control unit. There's the engine control ECU. There are ECUs for all the motors, the flaps, and the heating and ventilation, air conditioning unit. A lot of different ECUs targeting towards specific needs in the car. And all those ECUs, they can be of different sizes. They can have multiple processors. They can have heterogeneous processors, so processors with different speeds of different types, like CPU or GPU. And this not only relates to the processors, but also to the type of memory or the communication bus. Like if you have a control area, network communication, a CAN communication, a LIN bus, SPI bus, or whatever you have in the car. So it's a highly heterogeneous system consisting of many different ECUs and many different processors. And then there's the partitioning problem. I've covered this problem already in another publication, which is basically having in an early design process of some automotive software, you just have an amount of functions called runnables. That is one of the terms that I mentioned in the early beginning. Runnables are kind of atomic functions that cannot be distributed and form like the smallest computational units in your software. The partitioning problem covers grouping those functions, those runnables, together into tasks. And then, this is just a very small part, we have different tasks consisting of multiple runnables. And this is kind of the software model that we use. So we have tasks consisting of runnables. Those runnables have activation rates. They consume instructions. They can consume different instructions according to the type of processor they map to. And they access labels, so data that is mapped to memory. Okay? So, and from those accesses to the labels, the dependencies between the tasks are derived. So if one task writes a label and another task reads the same label, then there is a dependency between those two tasks, a directed dependency. So now, talking of the mapping problem, the question is, to what processor do I assign which task, right? So for example, you can put this task over there, the GPU task on a specific GPU, another task on some other ECU, and so on. So this is the mapping problem that we tackle, because this software distribution, the mapping problem, of course, influences response times, label access times, and many more, and all those timing constraints. And typically for a software developer in the automotive domain, it is very important that task deadlines are met, so that the response time of a task is never longer than, for example, the period of the task. Let's say if there's a task that is executed every 100 milliseconds, then when talking about rate monotonic scheduling, the deadline must not exceed those 100 milliseconds. If you have different scheduling approaches, of course, then there can be different deadlines. But this is very important. This is one of the constraints that we incorporate in our solution, which is holding the deadlines for all the tasks. And of course, there's also the problem of the label mapping. Where do I assign the labels to which memory? And this kind of generic mapping problem has been already studied years ago, and it's an NP-complete problem. So it's not solvable within polynomial time. So we need solvers or appropriate mechanisms to solve this problem. And when trying to solve this problem, a lot of questions occur. So how to derive the response times? How do we ensure that the deadlines are met? How do we ensure that we utilize the given resources as much as possible? And what about energy efficiency? Do we not only hold all the constraints in the system, but do we also optimize the system regarding response time? So if we see the hardware is capable of a lot of things, but we utilize it just to 20%, why not, as we heard in the keynote this morning, reduce the frequency of a core in order to still meet the deadlines, but save energy, for example. So those are a lot of questions that can be tackled during solving the mapping problem. There has been, of course, a lot of research and in this kind of mapping problem. And for example, there's usually many developers use integer linear programming in order to solve that. However, some of the recent research showed that ILP has scalability issues, and my measurements also show the same. That's why we try to have a look at other approaches than integer linear programming. We specifically had a look at constraint programming. That is what CP stands for, constraint programming. And like this publication shows that the constraint programming paradigm is very applicable to industrial applications. And of course, I will not go into much details because I do not have enough time, but you can of course have a look at my paper and read about the constraints that already have been tackled, but to the best of our knowledge, no publication was found that covered all the constraints that we identified for the mapping problem in the automotive domain. All right, so this is what we came up with. So we tried to identify a constraint programming approach. And another contribution that we provide in our paper is the formal outline of the different constraints in the automotive industry. And we solved the mapping problem, but we also solved the partitioning problem with the constraint solver as well. And what we compared is 6 different types or 6 different solver configurations. So the first one, DFG, stands for data flow graph heuristic. It's a greedy algorithm, basically, which tries to identify or assign tasks to the processor that is utilized the least. Then the first 3 solvers were given from existing literature. We also compare the integer linear programming approach and genetic algorithm, and they use existing libraries for those. And those are the 3 that we developed. First of all, just constraint programming approach that simply satisfies all the constraints. So there's no optimization involved, and it just satisfies all the constraints but does not optimize anything. The second constraint programming approach optimizes load balancing. So all the processing units in the system try to be equally loaded with tasks. It's the optimization problem. And finally, CPMO stands for Constraint Programming Multi-Objective. So there we optimize multiple goals, not only the load balancing, but also communication costs and response times. All right, now I have a couple of, or actually 3 slides that go into the math. I don't know to what extent this is interesting to everyone. I'll show them, but due to time, I cannot go into much details. So we have, of course, the instruction count for J stands for, is the index for a task, and I is the index for a runnable. So the instruction count for a task is basically the sum of all instruction counts for all the runnables that are within the task, which is derived from RA stands for runnable allocation. So runnable allocation is just a binary matrix, and it says if it equals 1, then runnable I is mapped to task J. Okay? It's pretty easy. And then we have the computation cost, so the execution time of a task at K is the index of a processing unit. Okay, so because the execution time of a task can vary depending on what processing unit it is mapped to. So it's basically the instruction counts of a task multiplied with this division. T stands for the period of a task, and divided by the processing unit capacity, which is usually given in hertz. I can make an example for that, but so basically if some task consumes 2 million instructions and it is executed every 100 milliseconds, then TJ is also given in picoseconds, so it's 100 times 10 to the power of 9. And divided, let's say, by 200 megahertz, that it's 200 in hertz is 200 to the power of 6. And then the computation time of that task will be 1 millisecond. Okay. And this is an example of a constraint that we incorporate into our solution. That means that of all tasks, so J is the task index still, and RA is the runnable assignment set, and we have, of course, many runnable assignments. And this is actually the constraint that we apply. That means that across all those runnable assignments, the period of the runnable must be all equal, must be the same for all J. That means that within a task, the activation rate of all the runnables that are assigned to that task must be the same. And this can be done not only for the period, but also for text, for software components. So all things that you want to pair together. You simply, in the constraint programming, you simply apply the all equal constraint. For example, according to the runnables, this equation says that a runnable must be assigned to exactly one task. It must not be 0, and it must not be 2 or 3 or other things. So we say that a runnable can only be contained in at most one task. All right. And similarly, you can use basically the same thing for the tasks, not only for the runnables. And then you use the K index, which stands for the processing unit. So a task can only be mapped to one processing unit. Okay, then there are a lot of other stuff. That's the formula where we derive the communication costs derived on the bit width of the channel that we use in order to access data in the system, and the excess latency, the excess cost between one processing unit and a specific memory type in the system or a specific memory location. And of course, we do not have everything from scratch. We use formulas that are already given in related work. Then this constraint simply shows that in the dot product of those scalars plus the communication cost that we calculate, which of course depends on the task allocation, so the task allocation matrix times the execution time matrix must be smaller than the processing unit capacity. So if, for example, we talk about the example that I mentioned earlier, if we have 200 megahertz, then, and we say, okay, we have 200 million instructions that we can compute within 1 second, then all the tasks assigned to that processor must not exceed 200 million instructions per second. All right? My time is almost over. So let's go to, well, I also have an algorithm how to derive the communication costs. I'm gonna skip that for now. And the things that we actually measured is the processing unit utilization, the communication costs, the speed of, and the solver runtime. The things that we were able to tweak were the model that we use, the solver type, as I mentioned earlier, and those three italic shown things were only applicable to generated models, because we used 6 models in total, 3 models from the industry and 3 models that are generated. We used the FMC environment that comes with the Alatea model, which is compliant to AUTOSAR. It's open source and used in the industry by different tier suppliers and OEMs. And we, of course, have assumptions like rate monotonic, fixed priority, preemptive scheduling, and label mapping is fixed, and so on. I mentioned that we have 6 models, and those are like the properties of the different models. Like they all have different type of processing unit. Well, not all have different processing units, only those, the generated ones and the demo car models have heterogeneous processing units. The FMTV model comes from literature, and this is an anonymized industrial model. Yeah, and these are a couple of properties the models provide, like different number of runnables, different number of activations, sequencing constraints, which is basically the dependencies between tasks, the amount of data that is accessed between the task and the processing units. And this, I hope you can, well, it's rather small, but this basically shows that this star that you can see over here, there, shows that it's almost in every case it's at the bottom, which means that the processing unit utilization is the lowest, because the star stands for the constraint programming approach for the load balancing. So, which basically shows that for all the different solver types, our constraint programming load balancing approach features the lowest utilization of the processing units. Yeah, and of course, like this triangle, the blue one is the constraint programming without any optimization, and the green circle is the data flow graph heuristic, and the genetic algorithm also performs very well. It's very close to the load balancing approach. Then we measured like the speed up, which we tried to scale with the amount of processing units that we couldn't configure for the generated model or the FMTV model. And we see that the speed up is the highest for the constraint programming load balancing approach. However, for, of course, no optimization and the multi-objective optimization, the results are pretty bad. And as you can see, the ILP curve over here and there was not able to find a solution at all within the fixed time of 5 minutes, which has been configured for those measurements. And for the multi-objective optimization, also for going beyond 16 processing units, the multi-objective constraint programming approach also was not able to calculate feasible results. The others do, though, and yeah, those are basically the results. We also checked the runtime, and of course the multi-objective optimization is the worst. And as you can see over here, also like the constraint programming approach raises. So as you can see, it is limited to 1 minute, the solver runtime over here. And the ILP solver also reaches the maximum at around 100 tasks already. And without optimization and the heuristic, the runtime is the lowest. And finally, those diagrams once again show on the left side the runtime, but this time not in line with the amount of tasks, but with the amount of processing units. And the ILP solver also scales pretty bad. And what is interesting to see here is that the constraint approach drops the execution time for 16 processing units, because there is just one single task in this model that defines the maximal execution time, and it cannot be further distributed. So after finding that this task is already assigned to the fastest processor, there is no more optimization potential, and the execution time drops to comparable execution times of the constraint programming approach and the heuristic approach. All right, so almost my last slide. This is just also comes from the paper directly. It just mentions that the constraint programming is a pretty nice paradigm to apply for optimization problems, because you have, as a software developer, you have a lot more natural definitions and modeling of the constraints, as you can see here. Different constraints, and they are basically very handy and very easy to use approaches in the constraint programming, rather than defining everything in your fitness function for the genetic algorithm, for example, or defining like linear inequalities only for the integer linear programming domain space exploration mechanism. All right, so what is the conclusion? Last slide. I'm almost in time. Yes, so the constraint programming methodology partially outperforms other domain space exploration mechanisms, but significantly eases software development and maintenance in the automotive domain. And it's very versatile, and it's a good paradigm to apply to industrial applications that we covered here in this research. And it also comes with early notifications to the programmer that there are, for example, contradicting entities that you have. For example, if you say that a task can only be mapped to one specific core, but the task consumes more instructions that a processing unit is capable of, then you have an early notification that there is a contradicting constraint. And of course, it's not only capable of providing feasible results, but only to optimize towards different goals. And we also show that the constraint programming approach is the quickest among ILP, genetic algorithm, and of course the load balancing optimization in the follow constraint programming. And the load balancing approach is of prior choice, especially when investigating constraints of non-integer nature. And in our cases, in 78% of all the measurements, the constraint programming load balancing approach performed or provided the best results. So that was a lot of information in a very short amount of time. Sorry for rushing through this stuff. Probably I would have needed a little bit more time. I also extended the amount of papers by pages by quite a lot amount. I had 12 additional pages. Maybe next time I have to pick a journal or something. I don't know. I thought it still fit here, and there were, since I had this reference marks here are, you cannot read it, I'm sorry. But in the paper you will find all the references that I mentioned in the presentation here. Please feel free to ask me any questions, and thank you very much for your attention.
Any questions? I have 2 quick questions. First one is about multi-objective optimization. What do you mean by solving multi-objective optimization problem? Because I thought that you get as a solution a Pareto front, so it's not a single solution, right? So probably
Yes.
By multi-objective optimization, what do you mean by that?
So for the load balancing, you have just one metric, that is the utilization of the processing units.
Yeah.
And in the multi-objective optimization, you not only have the load balancing, but you also have the communication costs,
Okay.
and so on. So usually when doing multi-objective optimization, you have a kind of Pareto front,
Exactly.
and from that Pareto front, you
So-
can
so-
pick which goal you emphasize more. If you equally load them, you rather pick
Yeah.
in the middle. If you weight them differently, you go to the corners of the Pareto front.
Yes, so what do you mean by the solution? Because you said solving multi-objective optimization is within a given bound. You mean this Pareto front is generated, or a decision which point to select from this Pareto front?
So for comparing the solutions in our literature, we equally weighted the optimization goals and picked like the middle of
okay.
the Pareto front.
Okay, so then it's no longer an multi-objective. It is
Well,
single
but the Pareto front is still available, right? So it computes the entire Pareto front,
Yeah.
and just for comparing purposes, we pick the one in the middle, but the others are given as well.
Okay. Okay, and then
But it's up to the programmer what to decide on which
point to select.
yes, point to select.
Exactly. Okay. And another is a very short one. There was a formula somewhere with 10 to the power 24,
Yes,
which
that's,
requires more than 64 bits to represent, which is quite unusual.
yes.
So how do you do that?
It was just a matter of simplifying the
Expression before.
the expression.
Okay.
So the formula comes from a larger formula where the exponents are at different places, and shortening this equation into a short term results in the equation shown.
So the denominator was just a variable, not a concrete number, but a variable. So I thought, well, it was,
Yeah.
but okay, it's clear.
Any more questions? Thank you very much. Our next presentation, mobile river navigation for smart cities, delivered by Kaunas.
I'll put back all the USB dongles things. It should put.
Password is, yeah.
Always the same problem.
Ladies and gentlemen, my presentation will be shorter, of course. And my name is Marta Włodarczyk-Sielicka. I work at Maritime University of Szczecin, and I would like to introduce you research the mobile river navigation for smart cities. It can be noticed that a lot of large cities all over the world have direct access to water, to open waters, like sea, oceans, lake, or river. And many examples can be given here, for like Amsterdam, New York, Szczecin, of course, or Hamburg. These cities are at the same usually important touristic hubs, touristic centers, with many attractions distributed on the area. So the smart transportation solution should be proposed for inland navigation. We proposed to look at the problem from water point of view, and we decided to describe our project, a framework of our project. It is mobile river navigation for tourists. Its name is MobiNav. The main goal of any navigation system on board of the vessel is to assist the navigator in the process of safety navigation. This is the most important. The inland navigation is similar both to maritime navigation and the car navigation, because the ship is navigate through the water, but the routes, the fairways, is like a street. So why not to use car navigation concept for inland navigation? It was the first question of our project. So the main features of our system are that MobiNav is for touristic users. It is a mobile application with suitable data sets, with a set of dedicated special analysis, with the advanced cartographic model. It was the most difficult for us, and it is integrated with social media. During working on building the system, we encountered many challenges. The main of them are performance challenges and cartographic challenges. For example, real-time system, integration of many sensors, both internal from device and external, size of data in maps, frequent change of situation on board of the vessel, small devices and many requirements, and the cartographic challenges, small screen of mobile phone and many information on it, frequently changing situation on our map, various user needs and preferences, changing scale of presentation of our map, and context change of required information, of course. Our system has a modular architecture. It consists of mobile application, server-side system, and can easily incorporate information provided by some external services or systems. The mobile application is designed to work in online and offline modes. It consists of 4 modules: the chat management, visualization model that is responsible for displaying maps, of course, special analysis module, and a sensor module that gathers and process data from other sensors, external sensors. The server-side part consists of 3 modules. 2 of them are related to to maps, to chart, and the user management module allows users to store personal data. When application is online mode, it can use several external systems. For example, AIS, it is Automatic Information System, Web Map Services, or River Information System. And okay, the last one, and the important. When we navigate in the city's river, we can also communicate with several smart city services. For example, smart traffic monitoring with automatic bridge and lock opening, yeah? Providing information about queues or time of opening the equipment. The basis of system are geodata from publicly available sources. We decided to use special geodata from 4 sources and data entered manually by the operator. The best sources of navigation data is electronic navigational chart, which are more and more common product in river city. So the data integration was necessary, and we create a new special model, MODEF model with 27 feature classes. And it's very important part of our system, mobile cartographic presentation model. It has been developed as a result of 3 basements: the traditional cartography, geographic information system presentation principles, and cartographic presentation methodology for land mobile location system. And our model is in general understood as a set of specified number of geocomposition and their components. The sensors, nowadays mobile devices have high quality sets of sensors, and many of them can be used for inland navigation goals, of course. Mobinav use 2 categories of sensors, sensor placed in a mobile devices where the application is installed. For example, compass, device orientation, geolocation, gyroscope or GPS, and sensor on board of our vessel of ship available through Wi-Fi connection. For example, EcoSander for bathymetric measurement, AIS, Automatic Information System, radar or weather station, some external. So the project was very huge, so it is the general concept, and in the last stage of our project, our system and commercial EGDIS viewer were compared. EGDIS, it is electronic chart display and information system. It is for maritime navigation. And on the EGDIS system, we use standardized electronic navigational chart, as we can see. Comparing the display of EGDIS system and our system, 2 routes were proposed for our ships. And the test area is included in Port of Szczecin, as we can see. And as part of the test, the navigation assistant, message display, geofencing, data visualization, and correctness of data model, of our new model, were checked. We conducted our test on board 2 ships. And at this stage, we checked and compared all components of our system. It was a very interesting time for us. And result and conclusion, when comparing 2 applications, you can indicate many common features. Both applications cooperate with external sensors necessary for navigation. Display of map and the similar is also the display of maps in various orientation modes. Ability to change colors due to external lighting conditions, and the display and colors of visualization is also similar because it is normal in for seamen for navigation, for maritime or inland navigation. Move on to the differences. It should be clearly stated that the Mobinav application has been extended with many new map layers, mainly related to tourist elements. An interesting solution implemented in new application is the navigation assistant. The well-known audio information module known from car navigation also works well on water areas, on water bodies. It is new part of system, of course. Our solution is also supported by processing of user data and allowing of the exchange between users. It is also possible. Next improvement is that user can have information about other ships even without having own observation sensors like radar or others. We can see other ships. And the next, Mobinav can be used in a mobile device. It was our first requirement. So tests and analysis performed in the research proved the usability of our system to inland navigation and for smart cities. Our product is modern, really modern. There is no something like this on the market now. The project is ended last year, was ending last year. Thank you for your attention. Only framework.
Any questions? Questions?
Like to know, is it the final commercial product or the prototype only?
It is now it's prototype. Yes of.
When you expect to commercialize it?
We hope in next year, but I don't know it will be possible because we use the data from publicly sources, and in Polish law it is simple, difficult.
How can you expect what could be the approximate price?
Oh, I don't know.
Okay.
But I don't think that it will be a lot of money. It's standard.
Another question. Who is the owner of the system?
Who is the owner? The tourist sailing on inland waters.
No, owner at the moment. So
Ah.
I would like to buy it from you and sell it in Holland.
Oh, no. Owner. It's, okay, not user, owner. It's owner, I don't know. Maritime Technology, the firm where we yes, Maritime Technology, okay. We did this project with a commercial firm, and it was, I think, the professor Stateczny will be the owner of our Stateczny. It is owner of maritime technology here.
And for which cities the maps are available?
Now for the Szczecin, of course, and the port of Szczecin and part of the river, Odra River, and for Świnoujście. Okay. Now, but our special data model can use each data from over the world, and is it is possible.
Does it require a lot of work to, let's say, support other cities, or it's
No, no. Now it's not a lot of work. It's only we need to special data, and we can convert it without any problem.
Seems we have no questions, so thank you very
Thank
much
you.
for the presentation. Do we have representatives of new paradigm of model-oriented control in Internet of Things? Seems we do not have. So was the last presenter. We conclude our session. Thank you. Can we proceed to lunch?